Alrighty. Well, welcome guys to the next edition of our Zoom Talk series. Tonight we have our guest speaker, Ken Hose. He is a retired electrical engineer from Intel. And in his retirement, he's become a much more active and very experienced amateur astronomer. He loves doing research projects with students, and he's actually going to be one of the mentors at this summer's Messier Field Station Astronomy Research Camp. I know I'm going. I think a couple other you guys are going as well. I'm really looking forward to it. And with that, Ken, if you have anything to add, go ahead. But otherwise, I'll hand it over to you.
Okay, yeah, just if you're going to turn over the screen to me, I'll share my screen and there we go. I hope this works. There. Can you see my screen, everybody?
Yep.
Yeah, I can see it.
Good. Okay, so I'm going to go through different projects that we could potentially do as amateur astronomers. I'm going to show you what my observatory looks like. Some people may want to come over and do some projects at my observatory, which would be just fine. But you know, maybe Messier Field Station is where we do our work. And then I'll talk a little bit about magnitudes just to review that, so we're all kind of on the same page. And then I'm going to talk about exoplanet transit detection and you know why you'd want to do that and how you can actually estimate some of the orbital parameters based on the light curves you get. That was what really got me started in the science aspect of astronomy. And then just a few random thoughts about searching for variable stars in random different star fields. And I'll present several different examples of variable star light curves. And then we'll talk briefly about the Hertzsprung-Russell diagram and its close cousin, the color magnitude diagram. That's kind of important. We can use that with star clusters to actually work out distances and even ages of the clusters. And again, we'll talk a little bit about Messier 3, which is a very dense globular cluster. And then I'll show an example of how we can work out the distance to open cluster M67 using main sequence fitting. And then I'll talk about some possible spectroscopy things we could do, just spectra of the typical different spectral types along the main sequence. And we could even do equatorial rotation velocity of Saturn and Jupiter using a fairly sophisticated spectroscope. So with that, we'll move on. Now, there's my observatory. I've got a pretty good southern exposure. As you can see, the roof rolls off, and there's a carbon tube telescope in there that I've actually replaced with a somewhat smaller telescope because it's easier to take on and take off the mount. But anyway,
Hey, Ken,
that's what it looks like.
Real quick, if I could interrupt. I only see the research projects for amateur astronomers, like your title slide currently. I think I see there's like your slides on the left that I think I'm not sure what's going on, but.
Does it look kind of funny?
Yeah, it looks like you're like still like, oh, there we go.
Are you in presentation mode?
I was in the, in the slideshow mode.
It looked like the slideshow mode wasn't working correctly. Yeah, because that you clicked that and it didn't change anything.
So far, nothing's changed on our end.
Okay. Well, how about this right here? Does this work out okay?
Yeah, that's fine. Just
okay. Sure.
Yeah, it works fine. It's just wondering.
Yeah, I don't know. You know, that slideshow mode hasn't worked for me for, you know, since there's been a Zoom upgrade or something. But anyway, so yeah, there's the observatory. And just a brief review on the magnitude scale. The real big numbers mean it's faint, and the negative numbers mean it's really, really bright. The limit of the human eye is probably around magnitude 6, apparent magnitude 6, and anything dimmer than that is really, really hard to see. And when we actually hook up our camera to the telescope and start taking images, what we get is instrumental magnitudes or raw instrumental magnitudes that come out from our software. And then we need to apply a correction to bring them up to some standard that everybody can agree upon. And typically we'll use maybe if we're lucky, there'll be a standard magnitude reference star somewhere in the frame that we can use to kind of calibrate everything and end up with proper apparent magnitudes. And the absolute magnitude is another measure, and that's the magnitude a star would have at 10 parsecs. And the little formula down at the bottom is important because we can use that to calculate the distance to a cluster, for example, if we know the absolute magnitude. But typically, you need to know the distance to a star in order to know its absolute magnitude. So there's sort of a chicken and egg thing here. However, with globular clusters and open clusters, we can kind of circumvent that problem and calculate the distance. And that term m, little m minus big M, is referred to as the distance modulus. And you'll find that in the literature all the time. Okay, so this cartoon depicts an exoplanet transit, and the little curve at the top is a light curve. It shows how the brightness varies as the planet transits across the face of the host star shown below. And the host star, of course, and the planet are in our line of sight, or the telescope's line of sight. So as the planet transits in front of the star, the brightness dims down and then it brightens back up again. And we capture that and we can create a light curve that we can use to deduce some information about the planet itself. So this is the approach we take. First of all, we point the telescope at the host star, and that requires that we know where in the first place, which I'll cover in a moment. Then we use a CCD camera to take back-to-back exposures, anywhere from maybe 60 seconds, sometimes less than that, up to 200 seconds or so. It depends on the brightness of the star. If the star is really bright, we'll use a shorter exposure so that we don't overexpose. And then we typically end up with, say, 150 exposures, sometimes over 200, but usually around 150 to 180. And a typical transit lasts 2-3 hours, but we always like to observe and record about an hour either side of the transit to get kind of a baseline. And we use specialized software to measure the brightness of the stars in our field. For each exposure, we measure the brightness of the host star, and we can plot that to make ourselves a nice little light curve. And then we can use other tools to fit the light curve to the data and use that tool to even extract orbital parameters for us, like the radius of the planet and its distance from its host star, that sort of thing. Here are some examples of transits that I've taken from my backyard. The vertical axis on the little graphs are magnitudes, and along the horizontal axis is time. I think these are all graduated in increments of about 0.5 hours. So the one at the top that shows a bunch of little blue dots, and those are my actual observations. So you can see there's some scatter there. And the pink is actually a fit, the best fit through all those dots. And you can see that particular transit lasts just about 2 hours. And then we image another hour or so either side of that for a total time of about 4 hours. And that particular exoplanet and star system is about 64 light years away from us. The one down at the bottom is 815 light years. That means light takes 815 years to reach our eyeballs from the host star there. That's pretty amazing that we can actually measure stuff that far away. And I'll bring your attention to the little matrix of measurement or information there. on the bottom, for example, we've got a magnitude 9.9 host star, and that we used, it's a fairly bright star actually, so we use exposure times of 60 seconds using a red filter, and that shows 260 exposures with about a 7 millimag dip in brightness. That's actually a fairly small dip in brightness, but as you can see, we were able to resolve that pretty well, although there's a fair amount of noise, a lot of scatter in the data, but clearly there's a transit in there. And according to my calculations, the orbital radius in astronomical units is about 0.058, which means that this planet is much, much closer to its host star than Earth is to our own sun. And the planet radius is about 0.94 times the radius of Jupiter. So we'll just say it's Jupiter size for the sake of argument. So how are we doing so far? This all making sense? Okay, so how do we plan for a transit? We don't just randomly point the telescope and hope we'll catch a transit. We will use web-based tools to find transits that are visible from our location. And this just shows the 4 different possible transits for the particular date and time I plugged into the program. And you notice this is for longitude and latitude 120 and 45. And those are approximately, the latitude and longitude right here where we live. And there's a bunch of information there that shows the depth of the transit and the magnitude of the host star, how long the transit lasts, and stuff like that, and the right ascension and declination as well, and the constellation. So anyway, that's what we use. So we'll look at this first, decide which transits we want, point the telescope, and then start imaging an hour or so before the transit. And this right here is a model, a mathematical model of a transit. It shows the big circle is obviously the host star, and the smaller circle depicts a planet which is going to transit across the face. And the little straight lines in the middle there on the bottom just are sort of a transit light curve decomposed into straight lines, where we've got the transit duration, we've got the duration of the flat part or the bottom part, and we've got the depth of the transit, delta F. And anyway, using these little geometries, we can actually work out equations for things like the orbital radius and the radius of the planet, the inclination of the transit, and so on, using those formulas down on the bottom, which are fairly straightforward. The one, the period squared one is Kepler's third law, and then the rest of them are fairly simple. So I'm not going to go into this, but I do have a presentation on this if anybody's interested in the math behind all this. And here's what's possible. Here is a list of several different planet transits in the backyard. And in the first 2 columns, you'll see orbital radius, so the distance between the host star and the planet. Calculated values, and the catalog values are values from, that are determined by professional astronomers, not amateurs like me. And you can see that for the orbital radius, how close my estimates have been to the catalog values. They're very, very close for the orbital radius. For the planet radius, they're pretty close too, but orbital inclination, there's a little bit more variation there. But anyway, the bottom line here is that you can make some measurements of a planet in another solar system that's hundreds of light years away, and you can actually measure like the size of the planets and how far they are away from their stars. I think that's pretty cool. I don't know about you, but anyway. So now, if there are no more questions about that, I'll move on to another topic. Okay. A hunt for variable stars. How many variable stars are in this field? Well, when we were at Pine Mountain Summer Workshop a couple of years ago, the last time we had it before COVID, we we detected the exoplanet Trace 3b in the constellation. I forget which constellation. I think this is in Hercules. And when we got home, I challenged one of the students to see if he could find any stars in the star field, because after all, I had, a couple of hundred images spanning 4 or 5 hours. And, if there was a variable star in there with a fairly short period, and there are lots of them with short periods, then maybe we should be able to find something. So we used a software called AIP for WIN, which was written by an RCA member, Richard Berry. And you all probably know about him. Anyway, this is what we came up with. We found a couple of eclipsing binary stars there. And these are both kind of interesting binary stars because they were fairly close binaries. The little cartoon over on the right that shows the two little blobs are depicted as what the star stellar envelopes would look like being distorted by the gravitational attraction because these two stars are so close together. The little red X there depicts the center of gravity for the system. And you'll notice that there's a nice clean light curve at the top, but the one on the bottom is just a little bit more scatter, a little noisier. Well, there's about a 10 times different in brightness. The one on the bottom is 10 times dimmer than the one on the top, and that just means that there's going to be more scatter in our photometry and our measurements. So it didn't really look quite as good as the one on the top. But one of the things you can determine from these light curves is the period. The one on the top has a period of about 0.32 days and about 0.29 on the bottom. So, and these are light eclipsing binary stars have different classifications, and you can look that up, but these are type EW. And the one on the bottom might even be a contact binary where, they're actually touching. So let's move along then. Here's another eclipsing binary. Now these would be really spaced pretty far apart. You'll see the primary eclipse on the left, and in the middle is the secondary eclipse, and so on. Now, I actually found this undocumented eclipsing binary by mistake in a star field for another exoplanet, HAT P8b. And I used this star as a comparison star, and what happened was my photometry all of a sudden went crazy, and I had to figure out why. And it turned out this particular binary system had started to go into an eclipse, and it totally trashed the light curve for the exoplanet transit. So I didn't find reference to this binary anywhere in the literature, so I contacted the American Association of Variable Star Observers, of which I'm a member, and talked to them, and sure it turns out this was one that hadn't really been documented yet. So I made a bunch of measurements over the course of a few weeks to work out the period and stuff like that, and that's a designation up at the top there, BD plus 34, blah, 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 blah. So anyway, sometimes just fortuitous things happen like that. The blue data points are my own data points, and the little turquoise and reddish sort of things are data from the Northern Sky Variability Survey that I think the AAVSO does. So anyway, that just helped complement the data. Okay, now here's another type of light curve. This is actually from an asteroid. So if you wanted to find an asteroid and take a light curve of that, yeah, that's possible. The reason why it looks kind of weird is because it's tumbling, and you're not going to see a nice regular sinusoid or anything like that. This is going to be a little bit strange looking. There's a little discontinuity in the light curve there because we just couldn't get enough data points over the 2 nights that we observed it. And then here's you see there are several different types of variable stars that they're broken into kind of like extrinsic and intrinsic. This is an intrinsic variable where the physics, the instability of the particular star causes the variability. In some of the others, the variability is caused by extrinsic things like another star or even an exoplanet transit is also considered a type of variable, but it's just variable by virtue of a planet transiting in front. Now this is a plot that was done up at the last summer workshop we had at Pine Mountain Observatory. This is the variable star XX Cygni. It's a pretty good one to do because it's got a very short period and you can do it all in one night. Now it looks like we combined the data from 3 nights for this particular plot, but that's also something you could do. So that just gives you a flavor of what you can do if you're interested in maybe trying to find and create some variable star light curves. You can actually determine some interesting physics by just analyzing the light curves. That we don't have time to go into that tonight, but anyway, that's enough about light curves and variables. So now we're going to talk a little bit about the Hertzsprung-Russell diagram, and this is kind of important because it shows how stars relate to each other in terms of their surface temperature and their brightness. This plot shows surface temperature along the bottom axis or the x-axis and shows luminosity or absolute magnitude along the vertical axis. And the solid red line there is the main sequence where stars are born, and eventually once they get old and use up all their hydrogen, they start to evolve off the main sequence and end up there in the upper right-hand quadrant. And some stars we know, like Arcturus and Betelgeuse and Antares, are all stars that evolved off the main sequence. So if we wanted to make a Hertzsprung-Russell diagram ourselves, we would need to somehow figure out what the surface temperature is of the stars. And that might be kind of difficult to do. And but I have a way, and I'm going to show you next how to get around that. And then another problem would be, well, how do we reckon the absolute magnitude if we don't know the distance to the stars that we want to put on a plot like this? Well, there's a way to get around that as well when you're dealing with star clusters, because they're all at the same distance. So you don't really need to know absolute magnitudes anymore. So let me talk a little bit about color temperature and how we can work out the surface temperature of a star without actually making a few simple photometric measurements. So the technique that I'm going to talk about now is basically called the color index. Take the color index of a star. And the whole approach is this, is you take an image using a blue filter and the visible spectrum, and another image of the same star using a V filter, which is actually in the green part of the spectrum. And you track the two brightnesses, and from that, that correlates directly to temperature. So just to look at this as an example, in the very middle is we've got the intensity actually on the y-axis and wavelength on the x-axis. And there are two stars depicted here, two spectra. One is a star that peaks in the ultraviolet and the other that peaks in the infrared. And in the middle there, the yellowish stuff, that's the visible part of the spectrum where we can deal with. Our cameras are most sensitive to the visible. So in this example here, the blue filter, it only it's fairly narrow in its bandwidth, so it doesn't take all the visible stuff, just the blue stuff. And the V filter just takes the green stuff, so that if we're going to get different values, different brightnesses through each of those filters, and that depends upon whether the star is a hot star or a cold star. Now, if B is brighter than V, if our B measurement is brighter than the V measurement, that means it's going to be a hot star. And if V is brighter than B, then it's going to be a cool star. So if you look over on the chart on the right-hand side, you can see how the B minus V measurements correlate to surface temperature and spectral type. And the B minus V number is actually called the color index. The color index. So in this particular case, the color index of minus 0.33 would be a really hot star, and an M in a 1.64 would be an M-type star, which would be on the very cool end of the spectrum. So hopefully this made some sense. Here's an example of a color magnitude diagram for an open cluster called M52. And we actually imaged this up at Pine Mountain and measured or calculated the distance to it. And along the vertical axis, we have apparent magnitude, and then we have that color temperature, the color index on the bottom. And let's see, this, can you see my pointer? I'm trying to point out something here.
Yeah, we can see.
Okay, good. Now let's look here at this. Does this remind you of maybe the main sequence? If we go up to here, we've got this main sequence which kind of goes, makes a diagonal from left to right going down. And so here's a color temperature of about 0.3. And let's see where that would be on the Hertzsprung-Russell diagram. Well, let's see, 0.3 is actually an F0 type star according to this. So if we go up here, where's F0? Oh, there it is right there. So that part of that color magnitude diagram that I just showed you probably is right about here. And it looks kind of like this too, doesn't it? Yeah. So I'm going to show you how we can measure and work out the distance to this particular cluster, or a cluster like it, in a moment. So let's explore star clusters here. The characteristics of stars in a given cluster are that they're all formed at the same time from the same material, and that's kind of nice because they're all at the same age. And they may have different masses, which mean they'll evolve differently, but they're all the same age. And they're all basically at the same distance. And the nice thing about these clusters are they're fairly bright, and they have well-resolved stars, and they're bright enough so that even in suburban skies here in Wilsonville, where my observatory is, we can image them quite well enough to do good photometry. And then we can make these color magnitude diagrams to work out the distance, and we can even work out the age. I determined the age of M67 using isochrones. I'm not going to go in there tonight, talk about that tonight, because it's kind of complicated, but that's one thing that's possible to do. And a lot of clusters also have variable stars, as you might imagine. Now, here's Messier 3 globular cluster. And as you can see, it's pretty rich. It's got, I guess, hundreds of thousands of stars. The little white box there, I'm going to show here on the next page. And the reason why when I'm showing this is I'm showing you where a lot of the variable stars are in Messier 3. M3 has got a lot of them. I think over 200 variable stars. A lot of them are our Lyriid stars, and most of them are blue. You can see all the stars that I've got the little arrows pointed to are bluish, and those are all variable stars. You can Google M3 variable star movies to actually see them blink. I do have a little video here I could show. Maybe I'll do it after we're done here, because I'll probably get something messed up when I transition from the slideshow to the video. But here are what those light curves look like for the variables in M3. I was actually able to count about 70 the variables in my little movie that I made, but as you can see, there are over 200 variables actually in that cluster. If you want to know more about how those are our Lyriid stars, the physics behind them, just Google Kappa mechanism or Eddington valve, and there'll be some information there on what causes these things to vary. And as you can see, the one on the right has about a 0.5, about a half a day period, a little bit more, and the one on the left a 0.3 day period. And you can see that they both average right around a magnitude, apparent magnitude 15 and a half, or a little bit more. And it turns out that that RR Lyrid stars can be used as standard candles, which means that if they have a fairly well constrained absolute magnitude, which is really cool because if we know the absolute magnitude and we know the apparent magnitude, which we know right here, I'm showing the averages, we can calculate the distance to this cluster using that distance modulus equation I showed earlier. Now it turns out that in globular clusters, the absolute magnitude varies from about 0.4 to 0.8, and that has to do with metallicity. There seems to be, from what I've been able to determine, a fairly linear relationship between the metallicity and the absolute magnitude. So anyway, I just looked up what the absolute magnitude was of the variables, our Lyrid variables in M3, and I got 0.58. So I plugged that into the equation and calculated the distance to M3. And it came out pretty close to what Wikipedia said, which is not too surprising. Okay, so there's an example of using the distance modulus to calculate the distance to a cluster. Now, here's a color magnitude diagram of M3, and you can see the evolution of the stars here. You see the giant branch, the red giant branch. You can see where all the RR Lyrid stars are. They're in this instability strip part of the Hertzsprung-Russell diagram, and that they're also in that so-called horizontal branch. Over on the right-hand side, you can see the professional color magnitude diagram, and notice that horizontal dotted line in both cases. That horizontal dotted line shows the magnitudes that are just too dim for me to be able to pick up properly in my small telescope. So compare everything above the dotted line on the two sides, on the two images there, and you can see that the color magnitude diagram that was done here at my observatory matches the one, the professional one, fairly well. So you can do real astronomy with, amateur gear like I've got. Okay, now let's talk about some open clusters. This is M67, and it's a very well characterized cluster. In fact, all the stars that I've labeled with letters are very well characterized, and they're considered, standard, reference stars. So the magnitudes, the B and the V magnitudes of the stars are very well known, and I can use them to calibrate my image. So here's a color magnitude diagram of M67, and you can see the main sequence there where I've got a red line plotted through there, and then you can see the turnoff point where the stars are evolving off. Those are the more massive parts of the cluster that evolve more quickly. They're evolving off, and then there's a small subgiant branch and then the giant branch up in the upper right. So how can we calculate the distance to M67? That's next. So bear with me on this, because the methodology might be a little bit difficult to understand, but let's see if we can work through it here. Now, the whole idea here is that if we can identify the little chart over on the right, the two columns show the color index for a main sequence star and the absolute magnitude. So all main sequence stars are for the given color index or color temperature are going to have a known and fixed absolute magnitude. So if somehow we can identify the same main sequence stars in our color magnitude diagram, we should be able then to work out the distance modulus, because we'll have some knowledge of the absolute magnitude. So the way we do this is through a process called main sequence fitting, where we try to fit a curve of the main sequence stars onto our color magnitude diagram. And the way this is done is we take the information over on the right-hand side, and we do the following. At the top, you'll see I have a notation there. We plot the distance modulus plus the absolute magnitude versus B minus V. So we have B minus V on our color magnitude plot, and we have it on that chart over on the right. So as an example, let's take the color index of 0.58, which is this little box right here, and the absolute magnitude is 4.4. So just for the sake of argument, let's assume that the distance modulus is 10, and we'll just add 10 to that, and that'll give us 14.4. So at 0.58 color temperature, we've got 14.4. So here's 0.58, and we go up to here. Here's about 14.4. So that's a dot right here on this red curve. So if we were to do the same for all the rest of this data, we would actually end up with this red curve right here. So let's do the same thing, except let's do it for 9.7 instead of 10. Or let's do it for 9.5 or 9.3. Do the same thing. And then when we find one of the lines there that really seems to fit where we believe the main sequence is, that's actually the distance modulus number that we can use to plug into the equation. So in this particular case, I'm claiming that this avocado colored line right here is really the best fit, and that's 9.7 distance modulus. I plug it into this equation here and calculate that the distance is 871 parsecs, which is almost 3,000 light years away. So does this make sense? I don't know. I hope it does. But anyway, I thought that was pretty cool. All right, now we'll shift gears. We're getting close to the end here. We'll talk about spectroscopy. Now, one of the things we did at one of my first Pine Mountain workshop is I had the students do some spectroscopy on each one of the main spectral type of stars, the OB, AF, G, K, and M type stars. And this is one of the spectra that they came up with. This was generated by the two students that I worked with. And the inset there shows the telescope. It's an 85 millimeter small refracting telescope. And this shows the spectrum for an A-type star, and you can see several prominent hydrogen absorption lines in there. And this is the star Zeta Aquila. It's in the constellation Aquila, I believe, and this is an A0 type star. And anyway, so this is an example of what you can do. Now, each of the spectral types is going to have a different look and feel to the spectrum. Some of them won't have these really deep, strong hydrogen lines, and some of them will have a bunch of weird molecular absorption lines from our atmosphere and stuff like that. So now, it's possible you can even measure the redshift of a quasar. In this particular case, I used this little filter here in the filter wheel of the camera. It just has 200 line per millimeter grating inside. And what that grating does is it tends to spread out the star image. And you can see that this arrow from H alpha is pointing to a little knot in this spectrum right here that's smeared out. That turns out to be a hydrogen emission line from the quasar. And if we look here, here's that hydrogen emission line right here. And here's a regular old star that's not being redshifted or anything. And there's the hydrogen alpha absorption line. And for this quasar, here's the hydrogen alpha emission line. So we're getting a redshift of almost 1,000 angstroms, which is really quite a lot. That was pretty cool. This is also the brightest quasar, and that's about the only one that's really easily accessible to amateur equipment. One other thing that we could do is we could measure the equatorial rotation velocity of a planet like Jupiter or Saturn. And that uses a little bit more sophisticated spectroscope over here. And there'll be a red shift and a blue shift depending upon which side of the rings you're looking at, whether they're coming towards you or going away. And you take the total shift there and you can plug that into the equation and calculate out the kilometers per second. And I was pretty close here with this calculation. So, summary. You could do real science with modest amateur equipment, and we can use light curves from exoplanet transits to estimate the size and orbital radius of the planets. And the light curves can help us understand the physics behind the behavior of these variable stars. We can show the effects of the stellar evolution using color magnitude diagrams, which are similar to the Hertzsprung-Russell diagram that you'll find in textbooks. And these star clusters have unique properties that allow us to make color magnitude diagrams, mainly the fact that they're at the same distance and same age. And we can dabble in spectroscopy as well as photometry and deduce properties of stars by their spectra. And just a closing note, I think that taking your own data and interpreting it can be really fun. I don't know what that was. Anyway, that's all I had. Open the floor to some questions.
I had a quick question about determining the type of variable star.
Yeah.
How do you do that? Is it just based on the light curve it creates when you take data points?
Yeah, pretty much.
Okay.
Yeah, the American Association of Variable Star Observers actually has a whole course that about variable stars, and they go through all the different types of variable stars, starting with the extrinsic and the intrinsic variables, and then from there it branches out into all the different subtypes. And there's some physics involved with how they put the different variables into the different classes. And I may have the handout for that if you're interested in. I can forward it to you. But anyway, the American Association of Variable Star Observers has got lots of information on that sort of thing. In fact, there's a whole organization just devoted to having amateurs take make light curves of variable stars and create databases and stuff like that. It's a very active organization. Any other?
Yeah, I got a question.
Yeah.
Oh, sorry to interrupt you. If you could go back to it was kind of one of the earlier slides about your exoplanet transits.
Yeah.
I noticed that the period for all the ones that you did was really pretty consistent between them. And
here maybe?
Yeah, here. So, and also I noticed there was radius. A lot of them are really similar. So I was wondering what the deal is with that.
Okay, now the period of these they're probably on the order of about maybe 3 days or so, and one of the reasons is that they're the easiest ones to find, because if you're taking images of the sky night after night, the variable stars you're going to see are the ones that have the shortest periods, right? And so it's sort of self-selected a lot, and these were done, before Kepler even, was up in the air, and a lot of the earlier periods and a lot of the earlier exoplanet transits were of stars that had a fairly short period in the order of 3 to 5 days. So yeah. Let's see here. Let's look. Does this have a period? I think. Yeah, here's periods here. This is a 2.79 day period. This is 1.32 days, 3.86, 4.46 period on this guy, So yeah, they're all in that area. And most of the ones with, periods like that too tend to be these big hot Jupiters too that we, the ones that at least are easiest for the amateurs like us to find. I don't know if that answered your question very well, but
Okay, I think it does, especially about like I was shocked about the planet the size of Jupiter that close to a sun,
well,
to a
yeah,
star.
in
So
fact, that's a good observation. That's what really blew people away when we first started getting data back from the first exoplanet transits, because it caused people to want to rethink, how planets formed, and our big planets are far away from the sun. How can this be within zero point zero 0.05 astronomical units from the sun? That just doesn't make any sense. So it really got people wound up. And of course, we're beginning to make some theories now, but yeah, it's been interesting to look at the demographics, as it were, of all the different planets. And now with Kepler, we've got such a wide range of planet sizes, periods, and so on that we're starting to develop a pretty good picture of what's out there. Any other questions?
Yeah, I'm curious. How does one go about reporting whatever data you gather?
Recording it, you say?
Like recording and reporting it so that other people can use your data to further whatever projects or just the general knowledge that we have.
Okay, yeah. Well, one of the websites that I use right here, in fact, it's this website right here. If you go to this website where you can find exoplanet predictions, you can also upload your own observations. And I've uploaded, like maybe, I don't know, 24 different observations that I've done. And when you do that, you get a light curve there, and some of the information you use, like the comparison stars you used, the telescope and stuff like that. So I've actually had researchers contact me and ask me to use my data that I've uploaded to this website. Apart from that, that's probably about the best answer I can give you right now. I mean, if you, for example, were interested in getting some of my data, I have all my data for every 200-second exposure I made of a given exoplanet, and you could take that data. In fact, I've got an example. I have a Google Drive page called Backyard Astronomy or Backyard Science, I think it is, and I've got data there for Exoplanet Transit Cutter 1B. And there's data there that you could actually use to practice with if you wanted to actually see if you could extract a light curve. I don't know if that answered your question.
Yeah, it did.
Okay. Any more?
all right, yeah, I've got one more. Well, at least one more. So you mentioned metallicity, and I'd never heard that word before, and I think it said it was like the ratio of iron to hydrogen. Does it have anything to do with how old the star
in
is?
astronomy, metal is anything that's not hydrogen or helium. And
Oh, okay.
yeah, and it's kind of weird. It's funny. So yeah, when you hear you're reading a technical paper, an astronomical journal where they talk about, metals or metallicity. Yeah, it's everything but hydrogen and helium, and yeah, they'll use hydrogen to iron, for example, a ratio as a way of depicting the metallicity. Yeah, that's correct. You said you might have another question?
Yeah. So you had your own HR diagram down there, and I was wondering, are all of those data points yours? Like you took every single one of those?
Yeah, yeah.
And how long did that take you?
Well, actually, software does it all. I have this program written by Richard Berry called AIP for Wind. I can extract either a single star, or I can extract all the stars, the photometry for all the stars in one go for on a given image. So what I'll do is I'll line up. Well, in this particular case, what I did was I took maybe 4 or 5 images from using the B filter, and then 4 or 5 images using the V filter, and then I'll combine them to reduce the spread and the scatter. So it's called stacking. So now I have 2 masters. I've got a master B and a master V. So then I tell the to extract the photometry for all the stars in the B and all the stars in the V. And then I do it in such a way that the coordinates of all this on both masters match up, so that when I get a column that shows all the B magnitudes and the V magnitudes, I can just simply subtract, the left-hand column from the right-hand column and use Excel spreadsheet to come up with the magnitudes and stuff for each star. So yeah, I just use a program that does it all automatically. So that, otherwise, it'd be pretty hard to do. But back in the old days, when they used photometers that were basically just like a diode or something like that, then they could only do it 1 star at a time.
Okay. Another thing, believe it or not, I might have spaced out when you mentioned this, but you mentioned the B and V sort of settings for gathering light, and you mentioned how they help you measure the temperature or color index of a star.
Yeah.
What exactly determines the B and V value? Are they were just chosen and that's how it is, or is there something behind it?
Well, back in the early days of astronomy, these guys that were doing photometry just settled upon a filter that would, they actually have a whole bunch of filters. They've got a filter, they've got probably 5 different photometric filters covering the really, towards the UV and then towards the IR. And so they standardized on the filter bandwidth and the center point of these filters early on in astronomy. So then everybody just started using them. Like Johnson, you've probably heard of Johnson-Cousins filters or something like that. And those were some standards. And then, modern day people use slightly different techniques to actually make the filters. And so they've had to adjust, their manufacturing process to try to emulate the pass band and the center frequency of those filters that were used, in the very beginnings of astronomy. So you can go back to data that was taken at the turn of the century with a V filter, and it'll be equivalent to that which we would take today, but it's just standardized. So. Let's see, was that kind of where you were going with that question? Or
yeah, exactly. So it's standardization, that kind of thing.
Yeah. And now, as long as I use, a photometric filter that's properly designed, then I will be able to get numbers that should match up to the numbers that, come from professional astronomers. When I showed you, let's see, there's... let's go the direction here. Right here. Notice that these numbers right here are determined by some professional astronomers, and they wouldn't have any meaning for me unless my filters were essentially the same as the ones used by the professional astronomers. Anyway, that's sort of like how things are standardized.
Okay, that's awesome. If anybody else has a question, it's cool, but I also have one more. So you talked about redshift in the quasar kind of at the end. Could you potentially calculate the distance to the quasar based on the redshift?
Yeah, you'd calculate the
Hubble law or
luminosity
something.
distance. Yeah, based on that redshift, right? Correct. It's called, it would be, decibel for luminosity distance. You can go Google that.
Okay, that's cool. Thank you.
Yeah, Google redshift of quasar 3C 273, and it'll tell you about luminosity distance. Yeah, because, these things here, the space is expanding, and that's what's really causing this redshift. It's not that it's, due to its speed necessarily as much as the It's just the expansion of space, and this thing is, way out there, really far away.
I have a question. Now, this.
Go ahead.
So I'm wondering, because let's say a quasar consumes a star of a different metallic composition or material composition, like an older star. Would the quasar shine a different color?
Excuse me a second here. I've got a phone call going on here. I need
no
to
problem.
tell my friend that I'll call him back. Hi, Dave. I'm in a presentation. I'll call you back. Bye. Okay, what was the question again? Sorry.
Okay, let's say a quasar consumes an older star, like let's say a star that's at the end of its lifespan and has a lot heavier elements in its core. Would the quasar shine a different color?
Well, quasars are actually not stars. They're actually the active
they're black holes that cause the
nuclei.
compression.
And they're powered by a black hole and an accretion disk around them. So I don't know if color would necessarily, let's see. Yeah, I'm not sure how to answer that. I don't know.
I was just wondering because I think they don't glow through fusion. They glow mostly through friction of the elements, right?
Yeah, I think that, yeah, absolutely. Yeah, that's the accretion disk. It's all those molecules and everything and atoms rubbing together inside in the accretion disk around the black hole. That's my understanding. I have a pretty tenuous understanding of it, to be honest.
I'm going to jump in there for a second. Ken, thank you so much. That was fascinating as usual. Students, if you want to actually do a research project with Ken, there's more than one opportunity, as I put in the chat. And if you have further questions that you didn't want to ask or you didn't get to ask, you can email them to me, and at a future in-person meeting, we can go more into depth on any of these. Or Charlie, I don't know the answer to your question. You could do some research and make a presentation to us on that. It sounds like you know a little bit about quasars. You could teach us a little bit about quasars.
Yeah, and if anybody is interested in this presentation, I can send you a copy of it, and you can mull over it and decide if maybe there's something there you'd like to do, either at the Messier field station or over here at my observatory.
Yeah, Ken, send me the PowerPoint, and I'll make sure that any student who wants it gets it.
Sure, will do.
Okay, Brennan.
Yeah, if there's no other questions, I think that'll do it for this meeting. Thank you so much, and that was a great presentation.
Okay, well, I'm happy to do it, and good to talk to you all.
Yeah. All right. I'll see you.
Thank you. That was really interesting.
Thank you, Ken. Bye. Thank you, Brennan. Bye.
Bye-bye.
Thank you,
Thank
Mr. Renata.
you.
Bye.
And meeting